Okay, in this assignment and in this lecture video, we're going to continue on our theory of how a TLC plate is working, how does it develop, what's going on with the HPTLC instrumentation that allows us to do this a little bit easier and a little bit better. And the first thing that we're going to kind of mention on this little bitty mini journey together is the chamber configurations. So what's going on inside of the chamber? And the chamber, well, that's like a chamber pot. No, that's not the chamber pot. That's something else back in the medieval times. The chambers that we are talking about is going to be really the area that we are putting the plate into. So those TLC, aka tanks, that we are using in a laboratory space, that is what we're going to refer to as the chamber. So I need to talk about the different configurations of the chamber, what's going on, how are they different, kind of what's the purpose of them, and being able to distinguish when is it appropriate to use and when it's not. So first off, we need to talk about the chamber configuration, and we've already mentioned this kind of term with developing solvent, and the developing solvent is what I am making in a laboratory environment and what I am mixing together. And then on top of the developing solvent, I'm going to pour that into the chamber, and when I do that, I'm going to put a lid on it, and we said that a gas phase begins to form. So I'm going to allow some time for the gas phase to generate and fill the upper parts of the tank. And then when that goes on, the developing solvent is slightly changing, and it's making the more appropriate mobile phase that is kind of staying in the bottom of that tank, ready for my plate to be inserted. So these are three terms that we've talked about. We've already mentioned them. We talked about the differences of them. We talked about the importances of them. Of course they are. Well, the chambers are going to be meant to allow this process to happen, and also to give me some options about how I want to develop these plates when I do actually place them inside of the chamber and put the lid back on them. But the only way that this can happen, that I get these choices, that I kind of have these different modes of what I would call development, is if these tanks are what we call twin trough. And twin trough tanks are probably the most common types of tanks that I'm going to be seeing out there in real life, in real laboratory settings. Now, I know that we've talked about the idea of, hey, if I'm a little cheapskate, I can use a beaker, and I can put my plate in a beaker and put a lid on it. Absolutely you can. That does not have a twin trough. We've also talked about these things called Copland jars, and we're like, okay, well, if you wanted to be a little bit fancy, but you don't want to go out for the prime steak, then okay, well, you go get a Copland jar, and the Copland jar is a little bit fancier with a lid that can screw on, or some type of, securing lid that can go onto the top, whether it's screw on or made in a different way. But it is the idea that I've got something and that is suitable for plate development. Most of the time, these are going to be for smaller plates, and these are not going to be appropriate either. That's not really what I see in real life. What I see in real life is a twin trough chamber. And the twin trough chamber is going to abbreviate it as TTC for twin trough. So these are the most common types of chambers. If you've done some labs already, I've probably already mentioned this in person about what these twin troughs are, what their purpose is, what they do, and so forth. And you've seen that actually, face to face. Or face to trough in this case. So what normally happens in the twin trough is that if I look down the side of the chamber, I see a little hump that's right here in the middle. And this gives me an area in the front, and it gives me an area in the back that I can play around with and that I can do stuff in. So with the twin trough chambers, there are times where both of these are going to be used. There's times where only one will be used in the beginning, and then we can use the other one a little bit later on, but we need to talk about these options and what they are. So normally in these troughs, you will have a rule of thumb, about 5 millimeters of mobile phase will happen at the very bottom of the tanks. So they're not squirting a lot of mobile phase in here. It doesn't need to be that much. 5 millimeters, folks, go take a ruler, look at 5 millimeters, not 5 centimeters, look at 5 millimeters. you'll see kind of, it just takes a little bitty smidgen of little liquid in the bottom of the tanks. And then this is going to be enough for that plate to suck up and for that plate to use in order to separate components from them. Now, keep in mind that based on the dimensions that we've talked about, as far as the monograph goes, there is a starting point on the plates. And these starting points were 8 millimeter from the bottom. So if I'm using some automated instrumentation, if that instrument is manufactured in a way that keeps these dimensions in mind, then we know that the pharmacopoeias and other types of regulatory sources will very often tell us to begin the band application at 8 millimeters high from the bottom. So by ensuring that only 5 millimeters of liquid is at the bottom of these tanks, then we know that we're not going to go over the start line. We know that when we dump the tank in, or the plate in the tank, that it is not going to go over our origination source, and it's not going to just seep out and go into the mobile phase and sit into the tank below. We know that that liquid is going to be below the sample application level. So that is why that's very often tightly controlled. We want enough in there in order for it not to go dry, but we can't put too much in there for it to go over the 8 millimeter mark. All right, so I first want to talk about unsaturated twin troughs. So with the unsaturated twin troughs, this is the idea that I can put the plate into one side of the tank. This has mobile phase down here at the very bottom. The plate or the chamber is not preconditioned. That is why we call this unsaturated. So immediately after we add the developing solvent, we put the plate on the inside and we put a lid on it, folks. That is what unsaturated is all about. So the mobile phase can still evaporate from the plate. The mobile phase can still escape. Gas phase can still get generated, but only after the plate is on there. We put a lid on it from the very get-go, and just whatever happens, happens. That is the idea of an unsaturated plate. Now, why do we use this? Well, we're going to use it mainly if the solvents that we are working with in our developing solvent are not highly volatile. So if we know that these components are not going to evaporate, if we know that they're not going to change over a course of time, then why do you want to waste 20 minutes for the chamber to get saturated with gas phase when it's not going to be making a big gas phase in the first place? So that doesn't make any sense. We want to process samples a little bit faster. And the way that we do this is use a unsaturated version. So that unsaturation will allow us to go ahead and add developing solvent. We know it's not going to evaporate. We know it's not going to go anywhere. We go ahead and dunk the tank into the developing solvent. We put a lid on it, and then when that development gets finished, it is finished. There is no preliminary wait time that is assigned here. Now, there's a couple of things that you got to keep in mind when you do this type of unsaturation type of method. Number one, you very often are going to get a higher RF value for all of your components in the sample. The reason for this is because the sample is normally soaking up through a dry plate. And there is a chance that that plate is going to be soaking that mobile phase up faster because it is dry. You know, it has not been preconditioned. It's not been placed inside of the tank. There's no gas phase that's going to be present. If so, very minimal. So all of the silica is going to be completely dry. Right? So then after I put the plate inside, it's going to soak up. It's like a piece of paper. It's going to soak up that water or that paper towel. It's going to soak up that liquid much faster using a dry one than it is a wet one. So because it does suck things up faster, then our RFs are typically a little bit higher as a result. Number two, very often these are going to take a little bit longer of a time, and I'm going to put in underline to finish. So in the beginning, it does suck them up very quickly, very fast. Gas phase is not present. The silica is not there. But, you know, over a course of time, as it pulls and it works against gravity in a way that capillary action goes up and up and up and up and up, well, the further we go up the plate, the longer it's going to take. We've actually seen this take place most of the time in our own type of situations that we are working with these lab experiments are concerned. So this is nothing like extraordinary. This is nothing that's unexpected. We actually have seen this in person. So in the beginning, it goes faster, and then as it travels up the plate, it begins to slow down a little bit longer, a little bit longer, and a little bit longer. Number 3, we actually have changes that can happen here a little bit easier, and those changes are going to be majorly impacted by the change in temperature and by the change of humidity. You know, this is not controlled. That chamber is not controlled. That chamber has not been placed a lid on. We're not doing anything with our humidity levels at all. It's just like, pour it in and put the plate in. Now put the lid on and go. I mean, that's what this is. So things are going to change. Things are going to fluctuate. Reproducibility is going to be a little bit more of a problem here in this case. So I'm going to put less reproducible. Again, I think that, gosh, I can't even spell today. That is supposed to be a deducible. So I think in the beginning, it looks very exciting. It's going to take off. It's going to kind of suck up very quickly. But then again, over time, and you've seen it maybe with your own eyes, things will slow down, and things will slow down quite a bit. All right. Next up, our other version or another version of development that we can have is something called saturated. And we can do a saturated development. And what happens here is that in this chamber, we get mobile phase on one side and we get mobile phase on the other side of that twin trough. So both troughs are going to be filled here with developing solvent. And then one is going to have a filter pad or a filter paper that's on the back side. So I'm just going to put FP for filter pad or saturation pad. Here, the lid is closed. So we put a lid on this thing after we place the pad in, after we place our developing solvent in. And then what we do is that, number 1, we are going to wait, and we're going to wait for about 20 minutes. That is the common rule that we kind of follow when saturation development is going to take place. We are allowing the equilibrium to take place here. So all of that developing solvent, it's got mobile phase components, and those mobile phase pieces are going to evaporate because some of them are volatile, and it's going to create a gas phase for us, and we're allowing that gas phase to be created first before we place our plate on the inside. So equilibrium is going to be kind of come to a halt at some point in time during that 20 minutes. We're giving it time for that process to happen, and then these components is generating that gas phase, which is going to help separation and which is going to help kind of latch onto the plate and do what it needs to do. But it is going to make our separation here a little different. So it is not a dry plate. You know, this is going to be placed inside of a tank, and that gas phase is immediately going to latch on to the surface of that silica that's on our TLC plate. So we start getting action in the upper realms of this plate before the mobile phase actually even reaches those areas of the plate. So that is how this is a little bit different than the time before, or the example before that we talked about with unsaturation. So saturated plates, again, look something similar to this. Both troughs are going to be used. You can see the filter paper or the saturation pad that's going to be here. That is promoting this gas phase to take place. Again, we wait for 20 minutes. We allow this process to go forward, and then we place our plate down on the inside. All right. As far as another different type of development that we can see, we can talk about something called preconditioning as well. So with preconditioning, what happens here is that only one trough is actually going to be filled with our developing solvent. And then there is a filter pad that is inside of that twin trough chamber, absolutely just like the saturation moment. And then on the other side, this is just going to be empty for now. And this is actually our plate in the diagram. So we put the plate with our sample, by the way, on the plate. We put our plate inside of the tank during this kind of wait period. So what's happening is that the plate is being lowered into the trough. That trough is empty. It has no developing solvent in it at all. There's actually no separation that's really going on with our plate. But what we're doing is that we're allowing our plate and we're allowing our samples to actually be a part of that kind of gas phase creation that's happening inside of our chamber. So what you're seeing is that the steps are telling you, okay, developing solvent's going to be poured into the trough, and we're going to put a saturation pad in. We're still going to go the 20 minutes, absolutely. We're going to allow this thing to do what it needs to do. And then it says a plate goes in front trough, and it's exposed to the gas phase for a total of 20 or 10 minutes. And then we add the developing solvent to the front trough. So that will come later, but this allows this plate to become exposed with the gas phase totally from, the top of the plate to the bottom of the plate before we allow the plate to dip down into the developing solvent, or AKA mobile phase here. So slightly different, but that is what a preconditioning is. So once more, we add the developing solvent into the chamber. We add the saturation pad into the chamber. We allow this process to take 20 minutes, just like it did before. We lower the plate into an empty trough, and then we allow that plate to get exposed to the gas phase for 10 minutes. That's most of the time, 10-minute time period. And then that gas phase is leaching and latching onto the surface of that plate, aka silica, or whatever stationary phase that you are using. And then we are allowing that plate to be exposed or to be preconditioned to the gas molecules before we allow the plate to begin the process of separation. After that 10-minute period is over, then we go back and we add the developing solvent into that trough, and we allow the plate to suck up after that. Some notes that we can use for saturated and our preconditioned versions of developing. Normally our RFs are a little bit lower here. Things are kind of what we would call pre-wet. And it's not a totally dry plate that can allow that initial kind of suction to take place all at one time. So our RFs are a little bit lower because of that. It gives us shorter times, less variation. It's more reproducible. So we're putting more control onto the idea of plate development. And that's really kind of where we dance around in a laboratory method most of the time. So for us, we're going to see a lot of saturation development. Very often do we see a preconditioned. We probably maybe will pull in one just so you can see how that process is going to work and how that process happens. But saturation, absolutely. So this is the idea. Again, we allow the tank to become saturated with gas phase from the developing solvent. So that way, when I put the plate in, that gas phase is already generated. It's already there. It's already ready to go. So that way, it's going to help improve the reproducibility of our separation time and time and time, day and day, a day again. So that's where this video is going to stop. In the next one, we're going to talk about the drying techniques that take place here at the very end. And then from there, we'll pick up.